Covalent bonding part 1. This covers how a covalent bond is formed, what a covalent bond is in terms of electrostatic attractions, drawing dot and cross diagrams for a variety of various molecules, understanding and explaining the physical state of substances with simple molecular structures. On the right, there are a few times shown to give you an idea of what is found where. Last time has somehow managed to randomly move itself, and it should be about there. Draw a sketch to show how a covalent bond is formed between two hydrogen atoms. Pause the video, have a go at doing it, and see how your answer compares to mine. So the first thing I would suggest doing is drawing two hydrogen atoms. Here you can see here we have a positive nuclei for one atom and the nuclei for the other atom here. And when they form a covalent bond, the two atoms will overlap, like so. Now, what are the key points of this diagram? So if we look at this diagram, we can see we have a shared pair of electrons. Now, what are the shared pair of electrons attracted to? They're negatively charged, so we attract to something positive. And here, if we label these two things here, these are the nuclei. And what's the relationship between the nuclei and the shared pair of electrons? These are the nuclei of the bonded atoms. So the attraction is between the bonded atoms nuclei and the shared pair of electrons. And what sort of attraction is this? It's a strong electrostatic force of attraction between the bonded atoms nuclei and the shared pair of electrons. So here are some sentences, or one long sentence rather. Can you pause the video, think about what you would choose as the answers, and then push play. So when you heat up, say, water, no covalent bonds are broken, it remains as H2O. So this is suggesting the force of attraction are strong. Obviously, it's a force of attraction because we've got positive nuclei and shared electrons, so it's an attraction. And it's between, and if we look at here, we've got a pair of electrons. So if we have a covalent bond, it will either have 2, 4, 6, or 8 electrons. So it's going to be pairs, and they're shared. These electrons which are bonding the two atoms together are shared between the two atoms. So it's going to be shared pairs of electrons, and the bonded, these are the two atoms which have been bonded. So the two hydrogen atoms which have been bonded together with a covalent bond, and it's between the shared pair of electrons and their nuclei. What is the link between group number and number of bonds formed? So if we think about it, we could do groups 4, 5, 6, 7, and 0. These are the groups which contain non-metals. And we could do, bonds formed. Group 4 forms 3 bonds. So for example, carbon. And it could form 4 single bonds, or it could form maybe a triple bond and a single bond, or it could form, say, 2 double bonds like so. An example, and then group 5, it has 5 electrons in the outer shell, so it can only obtain an extra 3 electrons in its outer shell, which could either be by gaining 3 electrons to form a negative ion, or by sharing electrons to form covalent bonds. So the number of bonds formed from everything group 5 is 3. So this would be nitrogen. It could form 3 single bonds, it could form a double bond and a single bond. Now we move on to group 6. It will form 2 bonds, so it could either form 2 single bonds or it could form a double bond. Group 7 can only form 1 bond, so for example it could be fluorine forming a single bond, or maybe chlorine forming a single bond. Group 0, the noble gases form 0 bonds. And the only one which is worth adding to this is hydrogen, which forms just 1 bond. So the key point is hydrogen forms 1 bond, so we could draw a displayed formula. So this is showing the 2 hydrogen atoms joined together with a single covalent bond. This is the only possible arrangement. The other way we could also do this is know that hydrogen exists as diatomic molecules, so as 2 hydrogen atoms joined together. We know that it's made up of 2 hydrogen atoms, each of which contain 1 electron in the outer shell. So for example, I've just drawn the 2 which would come together on each side, and when they come together they'll form a shared pair of electrons, and so the diagram will look like this. Chlorine is in group 7 of the periodic table, so it will have 7 electrons in its outer shell. We know it's also going to form a covalent bond. Covalent bonds are represented by atoms sharing pairs of electrons. So let's just draw both chlorines in. Let's start with this chlorine here and draw its 7 electrons. 1, 2, 3, 4, 5, 6. And the 7th one I'm going to put in here because at the very least it must have 1 shared pair of electrons. Let's do the same for the next chlorine and draw its 7 electrons. 1, 2, 3, 4, 5, 6, and 7. If we check, most things when they're formed covalent bonds will have 8 electrons in their outer shell, and this is achieved for both. The obvious exception is for hydrogen, which is obviously happy or stable with an outer shell containing 2 electrons. So hydrogen could be like this, and say chlorine could be like this, and that's hydrogen chloride. But apart from hydrogen, most things should have 8 electrons in the outer shell. Draw a dot and cross diagram for bromine, again showing outer shell electrons only. So one thing we could do is an alternative approach, is we know that bromine is in group 7 of the periodic table, and we know that everything in group 7 forms 1 bond. So here is a bromine molecule drawn with a line representing a shared pair of electrons. So now going from here, I know that bromine has got the shared pair of electrons here, and we know that each bromine has 7 electrons of its own in its outer shell. So 1, 2, 3, 4, 5, 6, 7. We could do the same for the other bromine. 1, 2, 3, 4, 5, 6, 7. Draw a dot and cross diagram for oxygen. So oxygen is in group 6 of the periodic table. That means it's going to have 6 electrons in its outer shell. So we could draw an oxygen here. 1, 2. Let's just draw it overlapping. We know it definitely would form 1 bond. So we've got 1, 2, 3, 4, 5, 6. We could do the same for another oxygen. 1 cross. Let's just draw it up. 1, 2, 3, 4, 5, 6. Now this diagram doesn't quite work because if you count around each atom, 1, 2, 3, 4, 5, 6, 7, each atom has only got 7 electrons in its outer shell, and we're aiming for 8. So if we removed this electron from here, this electron from here, we could put it in here like so. So now let's check 1, 2, 3, 4, 5, 6, 7, 8. So it has a full outer shell of 8. From here, we could obviously remember what a displayed formula looks like. Oxygen's in group 6, which means it forms 2 bonds. Each solid line represents a shared pair of electrons, so that means there are 2 oxygens with 2 solid lines between them. The other way we could also have done this is if we had been worked out this, we could have gone oxygen has bonded to another oxygen, and between the 2 oxygens are 2 double bonds, and thus how many electrons have we got left? 1, 2, 3, 4, 5, 6. This oxygen, 1, 2, 3, 4, 5, 6. So that's oxygen's dot and cross diagram. Nitrogen is in group 5 of a periodic table. This means it will form 3 bonds. If we do the displayed formula for nitrogen, we can see there are 3 there's a triple bond which consists of 3 bonds. Each bond represents a shared pair of electrons. So if we draw the 2 nitrogens together, cross dot, cross dot, cross dot. Let's see how many electrons we've got. We've got 6 in here. So we're probably going to end up with another 2 here. But if we think nitrogen's in group 5 of a periodic table, 1, 2, 3, 4, 5, 3 dots, 3, 4, 5. So we now have a dot and cross diagram for nitrogen shown. Draw a dot and cross diagram for water. The formula of water is H2O, and the arrangement of the atoms are, there's a hydrogen. Hydrogen only forms 1 bond, so this hydrogen cannot be bonded to anything else, so it must be bonded to an oxygen. Oxygen forms 2 bonds, so the oxygen will be in the middle and joined to 2 hydrogens. It's worth checking if you ever draw a displayed formula. It looks like this because sometimes I have seen HHO, and hydrogen obviously only forms 1 bond. So the next thing we could do is convert this into a dot and cross diagram. Let's put the oxygen in the middle. You can see there's a bond between the oxygen and hydrogen, so we could put 2 overlapping circles here. There's an oxygen-hydrogen bond here, so let's put 2 overlapping circles here and put a hydrogen here. In the middle, each solid line here represents a shared pair of electrons, so dot cross, dot cross. Hydrogen has a full outer shell with 2 electrons, so those 2 are happy, or have a full outer shell rather. Oxygen is in group 6, so 1, 2, 3, 4, 5, 6. So that's the diagram for water as a dot and cross diagram. The next one is ammonia. If you're not sure about the formula of ammonia, it is NH3, and there's something which is ammonium, which you may or may not have met, which is NH4+, but we're not worrying about that now. There's an interesting dot and cross diagram for this, which you'll meet at A level, and if you're interested, do feel free to ask. So we have nitrogen, it's in group 5 of a periodic table, it forms 3 bonds. Hydrogen only forms 1 bond, so we could obviously think that the displayed formula would look like this. Nitrogen is going to be in the center, bonded to 3 hydrogens. So we have 1 bond here, another one, oops, slightly poorly placed, 2, and 3. Nitrogen is in group 5, so it must have 5 electrons of its own in its outer shell. 1, 2, 3, 4, 5. So there we have a displayed formula for ammonia. Carbon dioxide. We could go through a displayed formula approach, which is what I will do in a second. The alternative, obviously, is if we think about overlapping circles. We know that carbon is here. We've got 2 oxygens here, and let's just assume we put a single bond in for each. Now, carbon's in group 4, so 1, 2, 3, 4. Oxygen's in group 6, so 1, 2, 3, 4, 5, 6. Do the same for this one here. 1 there, 2, 3, 4, 5, 6. Now if we count around for carbon, 1, 2, 3, 4, 5, 6, that's not enough. 1, 2, 3, 4, 5, 6, 7, that's not enough. So what we're going to have to do now is actually remove some of the electrons and share them. So, oops, I wonder if I can undo that. No, apparently I can't undo that. Okay, interesting. Wow. Okay, so let's rebuild that with my pen and draw the outer shell atoms here. Let's see if this works. So now let's try sharing an extra electron from each of the atoms. So carbon is now going to try sharing an extra electron with each of the oxygens, and each of the oxygens is going to try sharing an extra electron. Let's count round now. Oxygen has 8 electrons in our shell, carbon has 8 electrons in its outer shell, and as does oxygen. So that's a good diagram. If we did the displayed formula, we've got 2 shared pairs of electrons here. If we look here, we've got 2 shared pairs of electrons here, so carbon dioxide would look like that. If you remember that carbon is in group 4 and forms 4 bonds, oxygen's in group 6 and forms 2 bonds, it will be easier to go from here. So if I do it below, draw the carbons, the oxygens here, and put in my shared pairs of electrons, dot cross, dot cross, dot cross, dot cross. Carbon has obviously used all 4 outer shell electrons. Carbon never will have any unpaired electrons in its outer shell once it's bonded. Oxygen, well, there's one exception to that, but we'll come to that at another point in time if you remember graphite. Here we have oxygen, and let's fill its extra outer shell electrons in. 2 shared electrons, so it needs another 4 to go to get to 6, which is what group it's in. Oxygen here, 1, 2, 3, 4, 5, 6. So that's carbon dioxide. Methane, if you haven't done organic chemistry, the formula is CH4. Carbon is in group 4, so it will be forming 4 bonds. And anything we've got hydrogen in will have hydrogen joined to the other elements present. So that's our displayed formula. And if we draw our 4 hydrogens around here, 1, 2, 3, 4, dot cross, dot cross, dot cross, dot cross. So that's methane. Ethane has the formula C2H6. Again, when we're doing dot and cross diagrams, I would say ignore the hydrogen at first and go from that point. So we've got 2 carbons, let's bond the 2 carbons together. We've got 6 hydrogens, so let's draw the hydrogens in like so. That's a sloppily drawn hydrogen because the bond needs to actually be between the bond atoms to show it's actually bonded. So be very careful about doing that. This is really more true if you do A-level chemistry. So to convert this into a dot and cross diagram, an alternative approach, now that I'm happier maybe using rubber, we could think about the structure like so, and then draw circles around everything. Pen. I've just seen I haven't actually erased one of the lines. That's a bit silly. It's that one. There we go. And draw. Get my pen and draw overlapping circles. So let's start with 2 in the middle and draw the bonds for everything or overlapping regions of space. Let's draw our shared pairs of electrons. 1, 2, 1, 2, 1, 2. Not ideal. 1, 2, 1, 2, 1, 2, 1, 2. So that's a dot and cross diagram for ethane. Ethene gets interesting again, as in maybe a bit more challenge. Ethene has the formula C2H4. So let's do the same approach before. We've got the carbon, join it together, put the 4 hydrogens in, now carbon only forms 4 bonds. You can see here it's formed 3 bonds, so the solution to this is to put a double bond between the 2 carbons. So we can now convert this into a dot and cross diagram. For simplicity's sake, I will just redraw it. Dot cross, dot cross. Now I suppose someone could have maybe argued that the hydrogens aren't maybe symmetrically arranged. So you could maybe, I suppose, suggest maybe you had carbon like this with 3 bonds here, and this one here would only have 1 on. Now if you did that, you'd find this carbon here has got 2 things not bonded, so you'd find out through trial and error which diagram would work. Now the last dot and cross diagram is something called chloromethane. CH3Cl. Now don't worry about it yet, because if you've obviously done chloromethane, then it's relevant. Otherwise, I wouldn't worry about it. It looks just the same as methane, but instead of having a hydrogen in one atom, it's got a chlorine. So that's our displayed formulae. And what we want to do is convert it into a dot and cross diagram. So we draw it as overlapping circles. What's useful about this one here, dot cross, dot cross, dot cross, dot cross, is people sometimes forget to put the electrons in the outer shell for elements which are not hydrogen. So we've got our dot and a cross. Chlorine's in group 7. It hasn't yet got a full outer shell of 8, so we need 1, 2, 3, 4, 5, 6, 7. I find, to make sure I've done the 8, if I imagine positions of a clock, an analog clock, 12, 3, 6 and 9. If I put 2 electrons in at 12 o'clock, 2 electrons at 3 o'clock, 2 electrons at 6 o'clock and 2 electrons in at 9 o'clock, assuming obviously it's forming 4 bonds, this sort of rather helps make sure that I don't actually miss any out. The next section is looking at the melting points and boiling points of simple molecular structures. So explaining the physical state of substances with simple molecular structures and explaining the melting and boiling points of substances with simple molecular structures and what it's linked to. Substances with simple molecular structures are usually found in what state? A hint might be oxygen, argon and water. Simple molecular structures are usually found as gases or liquids. So what does this imply about their melting points and boiling points? This suggests they have low melting points and low boiling points. Why do you think this might be? Here is a picture on the bottom right showing iodine undergoing a sublimation. Think about the diagram, and are any bonds broken when iodine becomes a gas? The reason the melting points and boiling points are very low because only weak intermolecular, so forces between molecules, are needed to be overcome, which only requires a small amount of energy. No covalent bonds are broken, which are going to be strong. The next thing is, why do the melting points and boiling points of substances of simple molecular structures increase down group 7? This question could also be, why do molecules which are larger, why do larger molecules have higher melting points and higher boiling points? So if we look at the halogens, what information are we given? So it must be something to do with some of the data given. So if we look at the data given for fluorine, it tells us the relative atomic mass and also the atomic number. Now, the other thing we know is the formula of all the halogens. So halogens go F2, Cl2, Br2 and I2. Now we haven't covered this yet, but there's something known as relative molecular mass, which is where we take the relative atomic mass and we work out what the mass would be for the formula given. So if we've got F2, it would be 19 times 2, giving us a total mass of 38. Cl2, 2 chlorine atoms with a relative average mass of 35.5. So on average, one would have a mass of 35.5 times 2, giving us a mass of 71. Bromine, the relative mass would be 80 times 2, giving us a mass of 160. Iodine, 127 times 2 gives you 254. So we can see as we go down the group, the relative molecular mass increases, and this means they are going to have more intermolecular forces of attraction between them, which require more energy to overcome these weak intermolecular forces. If you do A-level chemistry, you'll look in more detail about the 3 different types of intermolecular force, and we'll find out a bit more detail about this.